Tonight on Orbital Estimate, we begin with a strange possibility. The moon may never be annexed. No president may step behind a lectern and declare that Shackleton Crater belongs to the United States. No Chinese official may stand before a red flag and announce sovereign control over a ridge near the lunar South Pole. No Russian spokesman may claim a permanently shadowed region by historic right, revolutionary destiny, or whatever antique imperial ghost has escaped from the basement of the foreign ministry. The treaty language is clear. Outer space, including the moon and other celestial bodies, is not subject to national appropriation. That sentence has carried enormous weight since 1967. It was written for a Cold War problem. It prevented the United States and the Soviet Union from turning the heavens into an extension of terrestrial empire in the most obvious way. It placed a legal wall between exploration and possession. It kept the flag from becoming a deed. The treaty did its job, yet tonight's episode begins with a colder proposition. A state does not need to own the moon to control access to it. That is the center of the episode. The next great power contest in space will probably begin through relay networks, docking standards, and safety zones. It will begin through spectrum filings, logistics nodes, cislunar tracking systems, and rendezvous-capable spacecraft loitering near assets that everyone claims are peaceful. It will begin through insurance terms and mission coordination rules written by people who use the phrase operational deconfliction without irony, which is how one knows civilization has entered its paperwork age. The moon can remain legally unowned while becoming operationally sorted into zones of advantage. Lawyers will insist that this is not sovereignty. Strategists will notice that it works rather well. Tonight we are looking at cislunar denial. By that, I mean the ability to raise the cost, risk, or uncertainty of a rival's movement across the Earth-Moon system without firing weapons, planting a flag, or formally violating the Outer Space Treaty. Denial is a familiar strategic concept. In maritime strategy, it can mean making a sea lane too dangerous or too expensive for an opponent to use freely. In air power, it can mean forcing aircraft to operate under threat. In cyberspace, it can mean degrading access, disrupting systems, or corrupting the data an operator needs to make a decision. In cislunar space, denial will have its own grammar. It will be slower, quieter, more technical, and more ambiguous. The tools will include space domain awareness, relay access, proximity operations, cyber intrusion, electromagnetic interference, safety norms, and liability exposure. No one needs to declare a blockade if every responsible operator quietly concludes that entering a contested zone is too expensive, too risky, or too politically toxic. That is the future we need to study. The first mature form of great power competition beyond geocentric orbit will be architectural before it becomes territorial. The decisive issue will be whether one block can shape the conditions of safe access across the Earth-Moon system. The side that can see farther, communicate more reliably, and define acceptable conduct will shape the rules of movement before anyone dares say the forbidden word: ownership. The treaty may hold, the architecture may decide. Let's begin where all sound space strategy should begin. We begin with geography, because geography is what turns ambition into constraints. It is what gives politics a shape. It is what tells great powers that their dreams still need roads, ports, and fuel. Cislunar space is often described as vast. That is true. It is also strategically incomplete. Distance is not emptiness. The Earth-Moon system has structure. It has recurring pathways, energy costs, gravitational features, communications limits, and timing windows that matter. It has regions where certain operations become easier. It has places where relay nodes gain value. It has places where surveillance has leverage. On Earth, geography is made of rivers, roads, ports, mountain passes, weather, rail lines, and choke points. In cislunar space, geography is made of energy. That is the first conceptual shift. A spacecraft does not move from Earth to the Moon the way an aircraft moves from California to Japan. Aircraft fly through atmosphere. They burn fuel, generate lift, adjust heading, and operate inside a medium that gives them continuous control. Spacecraft operate inside gravitational relationships. They change velocity at specific moments. They time burns. They enter transfer trajectories. They exploit orbital dynamics. They live and die by delta V. Delta V is the currency of movement in space. It is the capacity to change velocity. Every major maneuver spends it. Entering orbit spends it. Leaving orbit spends it. Matching another spacecraft spends it. Adjusting trajectory spends it. Recovering from bad navigation spends it. Moving from one useful orbital regime to another spends it. A spacecraft is a machine with a limited account balance. Spend unwisely and the mission becomes fragile. Spend too late and the window closes. Spend too early and later options disappear. Spaceflight allows men to speak in the language of discovery, majesty, and greatness. Then orbital mechanics hands them a receipt. This is why cislunar geography is strategic. Certain regions matter because they reduce costs or enable operations. Lagrange regions matter because gravitational relationships can create useful behavior. Halo orbits matter because they can support communications, staging, and observation. Near rectilinear halo orbit matters because NASA's Gateway architecture uses it as a staging orbit around the Moon. That choice is not random. A near rectilinear halo orbit can support access to the lunar surface while maintaining useful communications geometry with Earth. It can help crewed missions reach polar regions. It can serve as a node between Earth, lunar orbit, and the surface. It is a civil architecture decision with strategic meaning. A node placed in the right orbital regime can become a gatekeeper without becoming a fortress. It does not need weapons. It does not need armor. It does not need a dramatic name like Lunar Bastion, though one suspects that somewhere a defense contractor already has that slide deck waiting in a folder named Future Concepts. A relay satellite in the right place can shape communications. A depot in the right orbit can shape logistics. A tracking node in the right region can shape awareness. A staging platform in the right regime can shape who moves easily and who pays more. This is the second conceptual shift. Power in cislunar space will often be infrastructural. Control the relay layer and you influence communication. Control the tracking layer and you influence certainty. Control the logistics layer and you influence endurance. Control enough of these layers and you shape access while leaving sovereignty untouched. That is functional control. It is quieter than conquest. It is also more useful under current law. Now move from orbit to the lunar surface. The lunar South Pole has become the focal point because it may offer several operating advantages. Permanently shadowed regions may contain water ice. Nearby ridges may offer better illumination for power generation. Some terrain may support communications and repeated access more effectively than other locations. Some sites may be better suited for landing, excavation, mobility, and thermal management. This produces scarcity. The Moon is large, but useful sites are not equal. Some locations have better energy, some have better access, some have better communications, some have better proximity to resources. Some are better suited for building a repeatable operating pattern. Space policy often speaks as if free access answers the practical problem. It does not. Free access depends on coordination, safety, communications, and risk. A legal right can be broad while the operational path remains narrow. A state may possess the right to operate near a valuable site, yet still face relay dependence, spectrum conflict, plume risk rules, surface traffic restrictions, and insurance conditions that make the mission punishing. This is where cislunar denial begins. It does not require a blockade. It may look like a warning that a spacecraft is approaching too closely. It may look like delayed coordination. It may look like denied relay access. It may look like unresolved liability. It may look like a safety zone that is defensible in one case and coercive in repeated practice. It may look like higher insurance premiums. It may look like a close approach maneuver that forces a rival to spend fuel. The velvet rope will be made of orbital mechanics, communication standards, actuarial tables, and polite diplomatic notes. Less dramatic than conquest, more likely. Now let's move from physics to law. The legal foundation remains the 1967 Outer Space Treaty. Its basic framework is familiar to space lawyers, diplomats, and policy officials. Outer space is free for exploration and use by all states. The moon and other celestial bodies cannot be claimed through sovereignty, occupation, use, or any other means. That treaty solved a major Cold War problem. It prevented formal national claims over celestial bodies. It kept lunar conquest from becoming a legal extension of terrestrial imperial competition. It helped preserve the idea that outer space is a global domain rather than a new frontier for national annexation. Yet the treaty did not settle every operational issue. It could not. The drafters were not writing for a future in which several powers would operate relays, landers, rovers, surface power systems, lunar excavation sites, commercial logistics services, rendezvous-capable spacecraft, and rival diplomatic frameworks across the Earth-Moon system. They were solving the problem in front of them. The problem now is different. The Outer Space Treaty bars ownership. It does not abolish competition over use. That distinction carries the episode. A state may not claim lunar territory. It may still place equipment near a valuable site. It may not annex a crater. It may still create a safety zone around an active operation. It may not own a transit route. It may still define the standards needed for safe movement through that route. This is functional control without sovereignty. It operates in the space between legal principle and practical capacity. It preserves the language of open access while changing the cost of using that access. The Artemis Accords illustrate the tension. The Accords affirm the Outer Space Treaty. They commit signatories to principles such as peaceful purposes, transparency, interoperability, emergency assistance, registration, and deconfliction. They also introduce safety zones. That term is one of the most important phrases in the coming lunar order. Safety zones are intended to prevent harmful interference. That is reasonable. Lunar operations can be dangerous. Landing plumes can throw dust and debris. Excavation can disrupt nearby systems. Communications can interfere. Surface vehicles can create collision risks. Power systems can require standoff. Crewed operations introduce emergency concerns. A spacing mechanism is unavoidable. The issue is how such zones mature. A temporary safety zone around a lander during active operations is one thing. A persistent buffer around an integrated settlement, power system, relay node, landing zone, and extraction site is something else. The first manages operational risk. The second begins to resemble controlled terrain without the legal name. No formal claim is made. No sovereignty is asserted. No treaty article is visibly torn in half. Yet other actors may be told in practical terms to stay away. This is the strange genius of functional control. It preserves legal language while changing operating reality. Safety zones are not the only mechanism. Standards can produce the same effect. A coalition that defines docking protocols, communications formats, emergency procedures, navigation services, identification practices, and deconfliction expectations can create access dependency. New entrants may adopt those standards because the cost of remaining outside them is too high. The standard becomes the gate. No one calls it a gate. That is part of the charm. Markets can reinforce this. Operators working inside recognized coordination frameworks may receive better insurance terms. Operators approaching contested zones without accepted procedures may face higher premiums. Lenders may demand larger reserves. Investors may hesitate. Regulators may ask harder questions. Partners may step back. The state writes the rule. The market enforces the caution. No one salutes the underwriter, but he may decide who lands. This is why the future contest is architectural. The side that builds the default architecture for safe access gains power without needing territory. It can shape behavior through standards, infrastructure, financing, legitimacy, and risk. That is not conquest. It may still decide who operates. Now let's examine the American architecture. The United States is approaching cislunar competition through coalition architecture. Artemis is more than a lunar return program. It is a diplomatic framework, a technical standards effort, a commercial stimulation program, an alliance mechanism, and a strategic positioning move. It places the United States at the center of a growing space governance coalition. This fits American strengths. The United States has deep commercial launch capacity. It has a varied space industrial base. It has NASA's civil legitimacy. It has military awareness through the Space Force. It has allies. It has commercial firms that can move quickly, often faster than the bureaucratic digestive system prefers. The American model works best when it fuses government legitimacy, private production, allied coordination, and standard-setting power. That is what Artemis can become. It can become a coalition architecture. It can become a default access framework. It can become a system that makes American-backed norms feel ordinary before rival norms take root. This is subtle power. It does not require coercion at the start. It requires participation. A state signs the Artemis Accords. Its agencies begin using certain language. Its engineers plan around certain interoperability expectations. Its companies seek access to American-linked programs. Its diplomats learn the framework. Its insurers recognize the coordination model. Its mission planners assume certain standards. Over time, the architecture becomes harder to leave. This is where the United States has a deep advantage. It can create systems others join voluntarily because joining is easier than building a separate universe. That has been one of the quiet sources of American power since 1945. It is not always graceful. It is often bureaucratically maddening, yet it can be durable. Applied to cislunar space, this means Artemis should be treated less like a parade and more like an operating order. The United States must resist the temptation to define success through flags, photo opportunities, and ceremonial returns. Those matter. They inspire. They help sustain public legitimacy. The space program needs wonder because no civilization climbs upward by budget language alone. But wonder is not architecture. A lunar return without relay resilience is thin. A landing without cislunar tracking is fragile. A coalition without interoperable emergency procedures is ornamental. A standards framework without cyber discipline is a decorated door with no lock. The United States must build the system behind the symbol. Space domain awareness is central. The Space Force's doctrinal approach to space domain awareness already moves beyond catalog maintenance. It concerns the ability to detect, characterize, understand, and respond to activity in space. In cislunar space, that becomes foundational. Without awareness, proximity operations become ambiguous. A spacecraft approaching a relay satellite may be inspecting it. It may be conducting servicing. It may be rehearsing interference. It may be collecting intelligence. It may be signaling. The hardware alone does not reveal intent. This is especially true with rendezvous and proximity operations. RPO capabilities are useful for civil and commercial missions. They enable inspection, repair, refueling, assembly, life extension, and rescue. They are essential for a mature space economy. They can also enable intimidation, shadowing, sabotage preparation, co-orbital attack, and coercive signaling. The same capability can serve cooperation or coercion. That is, the dual-use problem. In cislunar space, this problem grows harder because tracking is more difficult, distances are larger, and assets are more expensive to replace. A rival does not need to destroy a relay to create pressure. It may approach closely, linger nearby, alter its trajectory in ways that force defensive maneuvering, or create uncertainty about collision risk. Ambiguity favors coercion. Awareness reduces ambiguity. That is why the United States and its allies need persistent cislunar tracking, civil-military sensor fusion, shared data standards, and public attribution procedures for unsafe behavior. Public attribution matters. In gray zone competition, evidence is power. If unsafe behavior cannot be shown, it can be denied. If it can be shown clearly, the coalition can respond politically, economically, and operationally. A rival can exploit silence. It has more difficulty exploiting a documented record that allies trust. The United States also needs redundant communications relay capacity. Communications will become the nervous system of lunar activity. Surface systems, crewed missions, robotic excavation, navigation, logistics, and emergency response all depend on reliable links. A fragile relay layer creates a tempting target. A resilient relay layer raises the cost of denial. The architecture should be interoperable across NASA, commercial providers, allied missions, and defense users where appropriate. It should avoid single points of failure. It should include cyber hardening from the start. It should be able to degrade gracefully under interference rather than collapse like a folding chair at a county fair. American weakness lies in fragmentation. NASA, Space Force, commercial providers, allied agencies, regulators, spectrum authorities, insurers, and contractors all have roles. Each actor has different incentives. Each actor has its own processes. Each actor has a reason to believe its spreadsheet is the main cathedral. This can produce gaps. The cislunar architecture cannot be a collection of admired objects. It must operate as a system. That means shared assumptions, clear interfaces, cyber baselines, emergency procedures, and cross-domain coordination. It means building the unglamorous parts before crisis exposes their absence. Prestige programs have a weakness for expensive shoes and forgotten maps. The United States cannot afford that in cislunar space. Now let's turn to China. China's lunar strategy should be understood as a counter-architecture. That phrase is important. Beijing does not need to defeat Artemis everywhere. It needs to prevent Artemis from becoming the only operating system for the Earth-Moon region. The International Lunar Research Station, led by China with Russia as a major partner, serves this purpose. It is presented as a long-term research presence near the lunar South Pole. It builds on China's lunar mission record and points toward a phased station concept in the 2030s. The ILRS gives China a parallel framework. It allows Beijing to organize partners, define standards, build prestige, guide technical cooperation, and create a political alternative to the Artemis system. The scientific goals are real. The strategic effect is also real. This is not a contradiction. Great powers often do useful science for geopolitical reasons. Telescopes can be sincere, so can ambition. The same mission can produce data, prestige, industrial growth, diplomatic leverage, and military relevance. A lunar base does not need weapons to alter strategic geometry. Power generation matters. Communications matter. Navigation aids matter. Autonomous surface systems matter. Cislunar tracking matters. A state with surface power, relay capacity, robotic systems, and logistics experience has a stronger position across the Earth-Moon system. Those capabilities can support scientific operations. They can also support civil-military fusion, surveillance, and strategic access. The same relay that carries scientific data can carry command links. The same tracking network that improves traffic safety can reveal rival patterns. The same proximity technology that services one spacecraft can pressure another. This is the reality of dual-use space. The line between civil and military significance is not always a line. Sometimes it is a fog bank with procurement officers standing inside it. China's broader space posture has become more capable and more assertive. Its rendezvous and proximity operations matter because cislunar denial favors states that can approach, inspect, shadow, or pressure rival spacecraft without destructive attack. A state that can maneuver near another asset can create leverage without crossing a clear threshold. That is useful in gray zone competition. The ILRS also gives China diplomatic leverage. Some states will prefer Artemis, some will prefer ILRS, some will try to participate in both where possible. Some will use alignment as bargaining currency. Some will seek prestige at lower political cost. Some will join Chinese-backed projects because they distrust American leadership, or because Beijing offers terms Washington does not. This matters because the cislunar contest will not be bilateral in a narrow sense. It will be coalition against coalition. The United States has the stronger alliance system. China has focus, state direction, and the willingness to build parallel structures when excluded from American-led systems. That gives the contest a long arc. Beijing does not need to claim the moon. It needs enough infrastructure, enough partners, enough operational presence, and enough technical standards to prevent the Artemis system from becoming the sole gatekeeper. That is the realist interpretation. The ILRS is not a science project with geopolitical side effects. It is a geopolitical project with scientific instruments bolted to it. That may sound severe. It is also how power works when a new operating region begins to matter. Great powers do not wait for markets to mature. They do not wait for legal clarity. They do not wait for diplomats to perfect the nouns. They build, they test, they coordinate, they create facts. Then they invite everyone else to describe those facts in polite language. The moon will be no different. Now we need to understand denial below the threshold of war. This is where many people get the future wrong. They picture lunar conflict as science fiction combat or peaceful exploration, with very little between the two. They picture bases with flags, dramatic weapons, or international harmony, lasers or conference panels. Humanity apparently has two moods in space: opera and paperwork. The real future will probably be more tedious and more dangerous. Cislunar denial will likely be reversible, ambiguous, and deniable. That makes it usable. Kinetic attacks are crude. They create debris. They invite political backlash. They can destroy expensive infrastructure that the attacker may also want preserved. They create escalation pressure. In cislunar space, where infrastructure will be sparse and costly, destructive attacks may be especially risky. Reversible pressure is more attractive. Electromagnetic interference is one option. Communications relay dependence creates vulnerability. Jamming can degrade signals. Spoofing can corrupt trust. Spectrum conflict can delay coordination. Signal degradation during landing, docking, excavation, or emergency response can create serious risk. A few minutes of interference may be enough. The mission survives, perhaps. The schedule slips. The operator spends more. The insurer notices. The rival has made a point without creating wreckage. Cyber operations are another option. Lunar systems will rely on ground networks, contractor environments, mission planning tools, cloud services, software-defined spacecraft functions, identity systems, telemetry pipelines, and command links. They will involve civil agencies, commercial vendors, defense users, academic teams, and international partners. The attack surface will sprawl like a bureaucrat's travel voucher. A rival may not need to hack a spacecraft directly. It may compromise a contractor. It may target mission planning software. It may manipulate tracking data. It may disrupt authentication. It may corrupt configuration files. It may steal operational data. It may quietly alter confidence. The effect may be delay, mission abort, fuel waste, unsafe maneuver, reputational damage, or insurance repricing. Cyber denial does not need to be spectacular. It needs to be well-timed. A small compromise in the right workflow can matter more than a dramatic intrusion into the wrong system. This is the dour little truth of cybersecurity. Attackers do not need to amaze anyone. They need access, timing, and a target whose process was designed by 6 committees and 1 exhausted contractor. Proximity operations offer a third path. A rendezvous-capable spacecraft can approach another object. That capability enables repair, inspection, refueling, assembly, and life extension. It also enables shadowing, harassment, intelligence collection, coercive signaling, and preparation for sabotage. In cislunar space, RPO can be especially powerful because the distances complicate tracking and response. A servicing craft near a relay satellite may create uncertainty. A spacecraft lingering near a depot may force a rival to maneuver. A close approach near a staging node may be described as inspection while functioning as intimidation. Again, no attack is needed. The weapon is uncertainty. Information manipulation can serve the same purpose. If a state can distort tracking data, obscure maneuvers, or create uncertainty about intent, it can force rivals to act conservatively. Conservative action costs fuel. It delays missions. It changes schedules. It increases risk. It affects financing. Uncertainty becomes a tax. Financial denial may be even more important. Space missions depend on capital, insurance, licensing, launch access, export approval, partner confidence, and regulatory clearance. A mission that becomes too risky may fail before it leaves Earth. A state can influence this through advisories, threat intelligence, export controls, licensing decisions, liability rules, diplomatic warnings, and public allegations. Insurers may raise premiums. Lenders may demand greater safeguards. Partners may hesitate. The rival has not blocked the mission physically. The mission has become financially radioactive. This is denial through cost. It is less photogenic than a missile. It is more compatible with peace. That is why it should concern us. Now let's return to safety zones, because they may become the legal center of gravity. The phrase sounds technical. It sounds responsible. It sounds like something designed by adults, which in space policy is sometimes true and sometimes a warning label. Safety zones exist to prevent harmful interference. That is a real need. A landing craft can damage nearby assets through plume effects. Lunar dust can be abrasive. Excavation can disrupt local operations. Communications can interfere. Rovers can cross into hazardous areas. Power systems may need protection. Crewed habitats require emergency planning. Nuclear power sources require strict standoff measures. No serious operating environment can ignore these issues. The problem is scale and duration. A temporary zone around an active mission is easy to defend. A persistent zone around a growing industrial site is harder. At first, the zone protects a lander. Then it protects a landing pad. Then it protects power lines. Later, it protects excavation equipment, communication systems, and emergency corridors. Each step may be reasonable. Together, they create a practical exclusion area. No sovereignty is claimed. Access is still technically free. The map tells another story. This is how the Moon could become operationally partitioned without formal ownership. The Artemis Accords try to avoid this by framing safety zones as temporary, transparent, and tied to actual operations. That discipline is essential. The United States should treat safety zones as operational instruments rather than proto-property claims. If Washington allows safety zones to look like lunar enclosure, it will damage its legitimacy. China will seize the argument. So will states that distrust American space governance. Some will object on principle. Others will object because it gives them bargaining leverage. Diplomacy contains many sincere statements, and some of them even mean what they say. American restraint is strategically useful. If U.S.-backed zones are bounded, transparent, and risk-based, then rival attempts to stretch zones into soft exclusion areas become easier to challenge. If the United States cheats first, it loses that advantage. This is disciplined realism. Legitimacy is a form of power when coalitions matter. It lowers the cost of cooperation. It helps attract partners. It gives commercial operators confidence. It makes rival narratives less convincing. It allows the United States to frame its architecture as open access under rules, rather than privileged access under branding. The deeper problem is the mismatch between formal equality and operational asymmetry. Every state has legal access to space. Not every state can build relay networks. Not every state can run cislunar tracking. Not every state can launch heavy payloads. Law provides the principle. Infrastructure decides how much the principle is worth. This tension is not unique to space. International politics has always had formal equality among states inside a world of unequal capacity. The difference in cislunar space is that capacity will be built early by a limited number of actors, and the practices they create may harden into expectations before a broad legal settlement emerges. Custom may outrun doctrine. Engineers may create habits that diplomats later translate into law. By the time the lawyers arrive, the landing pads may already have manners. That is why early practice matters. The first states to operate routinely near high-value lunar regions will shape baselines. They will define what counts as reasonable approach. They will define what counts as responsible coordination. They will define how safety zones are marked, communicated, and defended. The first operating culture may become the default. That is the strategic prize. Now let's ask what deterrence looks like in this environment. Cislunar deterrence will not resemble Cold War nuclear deterrence. It will not rest on one dramatic retaliatory threat. It will not be stable simply because weapons are absent. It will be built through awareness, resilience, attribution, norms, and credible response options. The first requirement is persistent cislunar space domain awareness. You cannot deter what you cannot see. You cannot accuse what you cannot characterize. You cannot coordinate around behavior you cannot explain. The United States and allied partners need tracking beyond geostationary orbit. They need sensors suited to cislunar dynamics. They need analytic tools for complex trajectories. They need civil-military data fusion, commercial participation, and allied sharing arrangements. They need enough public attribution capability to expose unsafe behavior without revealing sensitive collection methods. This is demanding. It is also unavoidable. If a rival conducts a close approach near a relay node and the United States cannot show what happened, the diplomatic response weakens. If a signal interference event occurs and no one can attribute it, the operator bears the cost alone. If a spacecraft maneuvers in a suspicious pattern and allied tracking is uncertain, response options narrow. Ambiguity favors the actor willing to exploit it. Awareness shifts the cost back. The second requirement is communications resilience. Relay architecture must be redundant. It must be interoperable. It must support civil, commercial, and allied missions. It must include cyber hardening from the start. It must support emergency procedures. It must avoid brittle dependence on a single node or provider. A coalition that depends on one fragile relay layer will eventually learn that the moon has majestic views and poor customer service. Communications are not a support function in the minor sense. They are the operating medium. Without communications, lunar activity becomes slow, risky, and isolated. Surface assets need command links. Crews need voice and data. Autonomous systems need coordination. Tracking data needs distribution. Emergency response needs reliable pathways. If a rival can degrade the relay layer, it can influence everything downstream. The third requirement is cybersecurity across the full mission architecture. This includes spacecraft, ground systems, contractors, cloud services, development pipelines, identity management, telemetry processing, mission planning, and cross-domain data flows. Cybersecurity cannot be bolted on after the mission architecture is already designed. That is how one gets a beautifully engineered spacecraft controlled by a ground segment held together by passwords, procurement exceptions, and a vendor portal last updated during the Bronze Age of JavaScript. The cislunar attack surface will be broad. It will cross agencies. It will cross companies. It will cross nations. It will cross classification boundaries. It will cross civil and military missions. That complexity creates risk. The answer is disciplined architecture. Strong authentication matters, command integrity matters, telemetry validation matters, ground segment defense matters, resilience under degraded conditions matters. The fourth requirement is norms for proximity operations. RPO is too important to ban and too dangerous to leave undefined. The United States should lead a narrow diplomatic effort focused on safe and unsafe rendezvous behavior in cislunar space. The goal should be operational norms that mission planners can use. Approach distances, notification expectations, and identification procedures should be defined before crisis. Emergency exceptions should be clear. Behavior around relays, depots, landers, crewed systems, and power assets should be understood before rival spacecraft create panic in the gray zone. Narrow rules are more useful than majestic declarations that nobody can apply. The fifth requirement is graduated response. If every unsafe act creates only two choices, ignore it or escalate dramatically, then rivals will operate in the gap. The United States and its partners need response options that impose cost without forcing immediate crisis. Public attribution, diplomatic protest, insurance advisories, licensing pressure, defensive maneuver, and coalition statements can all play a role. That is the art of deterrence in a gray zone environment. The goal is not to make cislunar space peaceful by wishing. The goal is to make coercion less profitable. Now we move into the stakeholder roundtable. For defense leaders, the first point is blunt. Cislunar space is becoming a strategic operating region before it becomes a mature commercial zone. That means defense planning cannot wait for a full market to emerge. The military relevance of cislunar space will come from relay systems, tracking, logistics, command pathways, proximity operations, and allied coordination before it comes from any dramatic weaponization of the lunar surface. The defense problem is ambiguity. A rival spacecraft near a critical node may be conducting inspection. It may be signaling. It may be testing thresholds. A communications disruption may be natural, technical, or intentional. A cyber incident may be criminal, state-directed, or both. A safety zone dispute may be operational confusion, legal assertion, or coercive probing. Defense leaders should prepare for pressure below the threshold of armed conflict. That requires playbooks. The United States needs to know how it will respond to a close approach near a cislunar relay. It needs to know how it will respond to suspected jamming during a lunar landing. It needs to know how it will respond to cyber compromise of a commercial mission that also supports allied operations. These questions should be answered before the crisis. Cislunar deterrence will be built through preparation. The most important defense investment is awareness. Persistent tracking beyond geostationary orbit gives commanders options. Without it, cislunar space becomes a theater of rumors. Rumor is a poor command system, though it remains popular in Washington. The second defense investment is resilience. The military value of a cislunar architecture depends on whether it can continue operating under pressure. Relay redundancy, cyber hardening, alternative pathways, emergency procedures, and allied data sharing all matter. If a rival can delay missions repeatedly without consequence, denial becomes attractive. If allied systems continue functioning under pressure, denial becomes harder. Resilience is deterrence when infrastructure is the prize. For commercial space executives, the message is sharp. Your lunar business case may be shaped by geopolitics before it is shaped by customers. That is not a pleasant thought. It is still true. Companies planning lunar delivery, communications, mobility, resource prospecting, power systems, navigation, servicing, or surface logistics will operate inside a strategic contest. Insurance, financing, licensing, export controls, cyber requirements, partner selection, and market access will all be affected by US-China competition. A company entering a contested lunar zone may face higher premiums. A company using one-block standards may gain access to infrastructure while limiting options elsewhere. A company with weak cybersecurity may become the easiest path into a larger architecture. A company depending on one relay provider may inherit strategic vulnerability without noticing it until the invoice arrives wearing a helmet. Commercial leaders should treat geopolitics as part of mission design. This means building for interoperability where possible. It means treating cyber assurance as a market requirement. It means understanding liability exposure. It means planning for contested communications. The opportunity remains real. Cislunar communications, power, surface mobility, precision landing, autonomous construction, navigation support, and logistics could become core infrastructure markets. Government demand will likely anchor many of them. Strategic value may arrive before pure commercial demand reaches maturity. That favors firms that provide trusted infrastructure. A company selling isolated hardware may win contracts. A company operating trusted access layers may shape the market. For policy leaders, the message is more delicate. Defend the Outer Space Treaty, but do not pretend it answers every operational question. The treaty's ban on appropriation remains essential. It protects a basic principle. It prevents crude sovereignty claims. It gives space law its spine. Yet policy must face the problem now emerging. Infrastructure can produce practical control without legal ownership. Safety zones can become persistent. Relay dependency can affect access. A sweeping treaty may sound attractive. It may also fail. Verification disputes, competing interests, strategic mistrust, and technical complexity will slow any grand bargain. A more practical path is narrow norm building. Define safe proximity behavior. Clarify safety zone expectations. Establish notification practices, set cyber baselines, develop attribution norms for unsafe conduct, tie rules to actual mission needs. In space governance, the perfect universal rule often arrives late, beautifully dressed, and carrying no tools. The useful rule arrives earlier with a checklist and a tired engineer. That is what the next decade needs. Now let's deepen the operational picture, because strategy in cislunar space can sound abstract until we place it inside a plausible sequence. Consider a future lunar relay network. At first, it exists to support science and crewed exploration. It helps missions near the South Pole maintain contact with Earth. It supports landers. It routes telemetry. It helps rovers send back data. It may provide timing support and navigation services. Then activity grows. More landers arrive. More rovers move. A surface power demonstration becomes a semi-permanent power node. A landing pad is constructed to reduce plume risk. A nearby excavation system begins testing access to volatile bearing material. Emergency procedures develop around the region. Commercial operators schedule surface missions around relay availability. At this point, the relay is no longer a nice accessory. It is part of the operating environment. Now imagine a rival spacecraft begins maneuvering near the relay's orbital regime. It does not attack. It does not jam. It does not issue threats. It performs what it calls inspection and characterization. The trajectory is close enough to generate concern. The intent is unclear. The operator must decide whether to maneuver the relay, alter mission plans, issue a public complaint, notify partners, or absorb the risk. Every option has cost. If the relay maneuvers, it spends fuel and may affect service continuity. If missions delay, operators lose time and money. If officials accuse the rival without clear evidence, the accusation may look political. If they stay silent, the rival learns that close approach produces little consequence. This is denial pressure. It is a test. The test is aimed at the architecture, not one object. The same logic applies to surface operations. A state establishes a safety zone around an active excavation site. The zone is tied to plume hazards, dust contamination, mobility routes, and power infrastructure. The claim is reasonable. Then the operation becomes persistent. The zone remains. More assets arrive. The operator expands the safety logic. Another state argues that the zone prevents access to an adjacent site of high value. No one has claimed sovereignty, yet the dispute begins to feel territorial. Now introduce communications interference. Signals degrade during coordination. The cause is unclear. It might be equipment failure. It might be environmental noise. It might be rival interference. It might be a cyber issue affecting ground routing. The mission slows. The insurer asks questions. Investors ask questions. Regulators ask questions. A later mission is delayed. Again, denial does not need to destroy. It needs to complicate. This is why cislunar strategy demands a systems view. A relay is tied to navigation. Navigation is tied to safety. Safety is tied to liability. Liability is tied to insurance. Insurance is tied to financing. Financing is tied to mission cadence. Mission cadence is tied to presence. Presence is tied to norms. Norms are tied to power. That chain is the real battlefield. The actor that understands the chain can shape access. The actor that studies only the spacecraft may miss the operating order forming around it. This is the kind of contest bureaucracies often struggle to see. They like categories. Civil over here, military over there. Commercial in another box, legal in a fourth, insurance in a fifth, cyber somewhere in the basement, where the fluorescent lights flicker and the best people quietly save the mission from the procurement office. Cislunar competition will cut across all of those boxes. It will reward states that can integrate. It will punish states that cannot. Now we move to the strategic forecast. Over the next 5 to 10 years, cislunar competition will likely move through 3 phases. First, standards, then logistics, then denial. The sequence matters. Standards will come first because actors need a shared operating grammar before dense operations begin. Docking interfaces, communications protocols, and safety procedures will shape who can cooperate with whom. Spectrum practices, emergency coordination, and debris mitigation norms will carry geopolitical weight even when they look purely technical. The side whose standards become ordinary gains leverage without needing formal command. That is the quiet wonder of architecture. It wins by becoming normal. The second phase is logistics. Relay deployments, lunar South Pole precursor missions, and surface power systems will make repeated operations possible. Precision landing, mobility networks, and cislunar SDA will create the conditions for routine activity. Once dependency forms, power follows. The third phase is denial. When valuable infrastructure exists, rivals will seek ways to pressure it. They will prefer reversible means. They will use electromagnetic interference, cyber operations, proximity pressure, safety zone disputes, legal ambiguity, information manipulation, and financial risk. The contest will not arrive as one dramatic moment. It will accrete. A relay here, a landing pad there, a safety zone, a docking protocol, a tracking network, a power source, a rescue procedure, a risk model. Each element will appear technical. Together, they will form order. That is the main forecast tonight. The moon will remain formally unowned, but operational advantage will cluster around those who build the access architecture. The United States has the stronger coalition and commercial base. China has focus, state direction, and a willingness to build a parallel system. Neither side needs crude militarization to compete. The contest will be colder, quieter, more bureaucratic, and more persistent. That makes it more likely, not less. The next great power struggle beyond Earth orbit will begin with practical questions. Who can move safely? Who can see? Who can communicate? Who must coordinate? Who defines irresponsible behavior? Who pays more to operate? Who writes the standards that later actors quietly adopt? Sovereignty is crude when dependency works better. The first power to master cislunar access may never need to claim the moon at all. So watch the quiet indicators. Watch relay contracts. Watch cislunar tracking investments. Watch lunar South Pole mission planning. Watch RPO demonstrations. Watch spectrum disputes. Watch Artemis diplomacy. Watch ILRS partnerships. Watch insurance language. Watch cyber requirements. Watch who defines normal behavior. That is where the contest is forming. The moon may remain legally free. Access may not. This has been Orbital Estimate. Stay focused on the architecture. That is where power hides before everyone else learns the name.